Perfect.
Our next speaker is Veronica Bitonti, who talks about numerical semigroups. Please.
Cool. Okay, so thank you very much, Mel, for allowing to giving me the chance to speak here today. And thank you everyone for coming. Oh, sorry, I need to move a bit. Okay, otherwise the light will just shut down. Perfect. And yes, so what I'm going to talk today is all joint work with Noah Kravitz, who is like now a postdoc in Oxford. And yes, as the title suggests, I'm going to talk about gap sets of random generalized numerical semigroups. So I guess in particular, the way I wanted to structure this presentation is like, first of all, I would like to like give some sort of like main definitions and like why we would be interested in these sorts of questions. After doing that, I will go with describing the main result of our paper, and then finally, I'll try to give some sort of proof sketch and open problems. Okay, so let's delve into this. Okay, so as I guess like more or less everyone knows what a semigroup is, but to be all on the same page, if we are working it with an abelian group G, then we say that a semigroup it's simply a subset of our group, which is also closed under addition. So easy examples would be the natural numbers, the even numbers, but the odd numbers are obviously not a semigroup because they're not closed under addition. Um, and in particular, when we're specializing our group, our abelian group to be the positive integers, and we are also interested in looking at a cofinite subset of it, and yeah, the zero is in it as well, then we call S a numerical semigroup. So in particular, because of this cofinite property, we can start of asking, I guess, some interesting questions about what is left outside of S with respect to the positive integers. And in particular, this like complement with respect of the positive integers is called the gap set. And two main notion about like the gap set of a numerical semigroup are the Frobenius number and the genus. So in particular, what these two quantities are representing is like one, which is the Frobenius number, is the basically the biggest value of a gap, and the genus is instead telling us what is the size of the gap set. And in particular, I guess this depends who you're asking, but if you personally ask me, I would say that things in combinatorics start to be even more interesting when we add some randomness into our picture. So in particular, let me shift this out. In particular, this was exactly what Delora, O'Neill, and Wilburn did in 2018 by defining the Erdős-Renyi model of a numerical semigroup. So as usual, they picked their probability P and they sampled then a P-random subset from the positive integers. And how did they do that? As one would expect, by picking positive integers with probability P and independently. And then they obtain a semigroup by basically closing it under addition. And in particular, a thing that I would like to emphasize here is that by doing this operation of closing under addition, summands are allowed to be the same. So these A1 up to AK, they can all be the same value, basically. And the reason why I'm saying this is because in a couple of minutes, a couple of slides, it would make sense when we're going with our main result. But okay. And in particular, what they did in their paper was, okay, we have started to add some randomness into our picture. We defined this like this random numerical semigroup. So we can still, we can still ask questions about what is basically the gap set. So what's going to be the Frobenius number for the gap set? What is going to be the genus? And in particular, this is exactly what they did. In expectation, they showed that the expected size of the gap set and the expected size of the Frobenius number is somewhat in between P inverse and P to the minus 2 up to some constant values. And later on, by Borgat and Morales in 2025, it was improved the upper bound to P inverse to the log P inverse cubed. And in the same year, Kravitz, Morales, and Schildkraut showed how actually both the lower bound and the upper bound are roughly p inverse log p inverse to the power of 2. So up to some constant value, the result about the one-dimensional case, about like the Frobenius number and genus of our gap set is basically solved. We know exactly what's the shape. And actually, they prove something even stronger, for which this expectation became like a corollary of it, which is the corresponding with high probability result. So in particular, they showed that if we are picking our density P random set A from the positive integers, and we're closing it under addition by therefore defining the corresponding numerical semigroup, then with high probability, we have that the genus and the Frobenius number, so the size of the gap set and the largest element in our gap set is roughly p inverse log p inverse to the power of 2, up to some constant value. Okay. However, all what they discussed was like by working over the positive integers, so by working on like a sort of 1D scenario. However, as they also as Kravitz, Morales, and Children asked, they were interested in what was going on in the higher dimensional scenario. And indeed, if we specify now our group to be the integers in dimension bigger than 1, and we are now picking a cofinite semigroup S that contains the 0, then now we can also consider here a numerical semigroup, which we will call generalized numerical semigroup because we're working in higher dimensions. And in particular, we can do a similar thing for the random case by, again, looking at what it would be in this case, the multidimensional Erdős-Rényi model. So again, by picking a p-random subset of the ZD, where every element is positive or negative, and then we allow it to be closed under addition, where again, the summands are allowed to be the same. And by doing this, we can again ask questions about what is left, what's outside our semigroup S, so in particular, what's happening in our gap set. However, we need to do some briefly consideration here because we have to note, first of all, that the Frobenius number, as we defined before, that cannot be defined basically in the same sense, because in the one-dimensional scenario, the Frobenius number, what was it? Was the size of the largest gap element. Here, this notion of largest, what does it mean? We do not have a unique definition about it. However, it does still make sense to look at what's outside our semigroup and count what's the value of the gap set, exactly the size of the gap set. Okay. And in particular, another thing that we can talk now, being in a higher dimensional scenario, is actually what is the shape of the gap set. So what do I mean with shape? Well, because we are now working for a dimension bigger than 1, we can expect to have regions in our hyperplanes where we do not have many points of our semigroups, and region that instead have loads of points of S. So I guess the question in this case would also be, is there perhaps a sort of threshold shape that is distinguish a part of our space that does not have many points of the semigroup and the part of space that has instead loads of points of our semigroup. And this is exactly what we were able to do with Noah, because in particular, we were able to show how this scaling limit for this gap set is exactly some element of this shape. So in particular, what is this, as I said, what is the scaling limit? Is this curve that in our case is of this form that is basically kind of describing what is happening in a region of our plane that is there's no many points of S, and the corresponding region above that curve that instead has many points of it. And I think that what we would like to note about the scaling limit is how this is saying that this sort of threshold shape is an hyperboloid, and this should make sense. This does make sense. And why it makes sense? Well, because if we look at a particular point in our space and we want to see whether this point is going to be a gap element or not, well, this is more or less equivalent to looking at box that this point is basically generating by looking at the projection of such a point on the different planes. And in particular, this point would not lie on the gap set, would lie in our gap set if we have that all the generator of the semigroup that do not lie in our box. So in particular, the probability for this to happen is roughly roughly 1 minus p to the volume of our box, because p is the probability of selecting any point, so the probability of not having a point is 1 minus p, and this is roughly exponential to minus p times the volume. And again, this sort of threshold passing from the probability of being 0 to the probability being almost 1, this threshold is happening exactly when we have that the volume is roughly p inverse. So ignoring for now the shift of a log p factor, this is exactly what it's telling us, that the volume is more or less roughly p inverse. And this shift by a log p inverse factor is because near the coordinate hyperplanes, we want the lower dimensional behavior to be the one that is dominating, whereas when we are away from the coordinate hyperplanes, we would like the full d coordinate product to be instead the constraint that dominates. So that shift allowed us actually to describe basically the scenario exactly like this. So being able to consider separately the case near the coordinate axis, the coordinate hyperplane, and away from the hyperplanes. Okay, and more formally, to be able to describe our main result, let's consider for now any integer, positive integer z, which for us in particular would be of the form p inverse log p inverse d plus 1, which again, as an aside, it should also make sense that we have a form like this, because this is also kind of generalizing the one-dimensional scenario. Because in the one-dimensional scenario, the power of the log p inverse was simply 2, whereas here, being in d dimension, it makes sense to expect that the power be d plus 1. And so in particular, we define with RdPz to be exactly this. So we are taking our hyperboloid, and then we're looking at all the region that is below that. So by putting z to be, as I said, this value here, this p inverse log p inverse d plus 1, this is exactly describing all the points that lie below our hyperboloid. And so in particular, what our main theorem is saying then is that, again, if we consider any dimension that we like, then we can find a constant that depends on the dimension, a positive constant, that for which the following holds. So if we sample, as we have said before, a p-random subset A, and we look at the corresponding numerical semigroup, random numerical semigroup, then with high probability as p tends to 0, we have the following cases. So we have that with high probability, what is below our hyperboloid region, in this region, the semigroup S is kind of sparse, whereas above the curve, our semigroup S is really dense. Our random semigroup S is really dense. And in particular, with these two information, we were then able to define, to find the actual value of the shape of the gap set, well, those were describing the shape, and then to find the exact value of the size of the gap set, which is roughly p inverse log p inverse to the power of 2d, up to some constant value. So in this picture, this is describing exactly what I said. So as we can see here, below our, I guess, more pinkish curve, this is telling us that below that we are not expecting, there's not, with high probability, there's not many points of our semigroup, whereas above this purple shape curve, we have that the semigroup S is really dense. And the only difference between the two curves is this constant value that is changing, but up to this constant value, we actually know now we have a precise definition, a precise value of this scaling limit. And why I was remarking before about the definition of a numerical semigroup to allowing summands to be different, well, because if we instead to be the same, is because if we restrict the case now and imposing that the summands are actually always different, then it would be equivalent basically in looking at the finite sum of A, where this is like as we expect. So we are again selecting our p-random subset A, and now we're looking rather than at the numerical semigroup at the finite sum generated by such a set. So in particular, looking at all the possible finite sum where the summands are now different. And even in this scenario, then we get that our theorem holds exactly in the same way. So by just changing our random semigroup with our random finite sum, we obtain basically the same result. Okay, and I guess I should have a bit of time to go through the proof sketch and then describe some of the open problems. Sorry. Okay. So let me do exactly that. So I guess the first thing would be showing the first point of our main theorem, which is like showing that S is sparse below the hyperboloid. And this is equivalent in giving a lower bound on the gap set of our gap set S. So in particular here, the proof was motivated a lot by the one-dimensional case, but we needed to add some new mix of geometrical and additive ideas. And in particular, the whole main point of our proof for this lower bound case is this key lemma that is coming from Maynard-Duss from the 1950s, which is giving us the ordinary generating function for the partition for these colored integer partition. So what did Maynard-Duss mean with that? It means that if we have a sequence of non-negative weights, and we are now looking at like the integer partition of n, where each part of a fixed size k comes now in new k different colors, then by letting part un to be that number of the total number of such a quantity, then the ordinary generating function can be described as explained here in this theorem. And in particular, we have that the constant is an explicit constant. So this was for us then the main result, because with this in mind, we were able, as I said, to prove the lower bound. So how did we do that? Well, what we did is like, we first of all realized that this RDPZ shape, which as we should recall, this is basically by looking at our limiting shape and then our limiting hyperboloid, and then just looking at all the points that lie below that. Well, this can be estimated by a union of theoretical regions. So now the question is not by looking at the sparsity of S within the whole region below the hyperboloid, but actually by looking at the sparsity of S below each of these tetrahedral regions. And once we have done that, then we did the sort of like additive reduction. And what do I mean with that? Well, again, rather than looking at the whole gap set, at the whole numerical semigroup, random numerical semigroup S, we also partitioned that accordingly to when points were or were not on the axis. And this is where this like being away from the axis is coming from. This extra log p inverse factor is coming from into our picture. So in particular, we look at the generating set A, and we're now, as I said, partition this into set AIs such that each of them is made of points that do not lie on the axis. And now we're looking at we're closing this under addition, and we're looking now at the numerical semigroup generated by each of these AIs. And now is via this Maynard-Duss asymptotics that we are able to say that with very high probability, each of these AIs closed under addition are now sparse in our tetrahedral regions T. And with that, we can then it follows that by taking a union over all the different AIs at first, and then over all the different tetrahedral region, so taking a double union bounds, we're able to say that indeed S with very high probability is sparse below the whole hyperboloid region. Okay, and differently, we then had to look at the upper bound, and here instead the goal is basically the opposite. So we want to show that our random semigroup S is instead dense above our hyperboloid region, and in particular, this will give us now an upper bound for the gap set. And how did we do that? Well, again, rather than looking at the whole, well, here we're not looking at what's below our curve now, but what's above. So this would correspond by looking basically at the complement of our region RD with respect to ZD. Rather than looking at that whole region, it might be actually useful to look at subset of it accordingly, again, to how many coordinates as well. So again, by taking into account how far we are from the axis. So this is exactly, as I said, what we did. So now we are looking at this region that for simplicity, we would call it U. And then we are splitting it in UIs, where each of these UIs is made of is taking into account how many coordinates are small, so are close to the hyperplanes. And we then, for each of these UIs, we notice how they like in the union of regions that look exactly as described here. And in particular, these capital YI are exactly going to be those log P inverse factors. So this is exactly telling us that each of these regions can actually be seen as a union of other region Ws that are taking into account how the points are actually far away from the axis, how far exactly that log P inverse factor. And we then had this idea of this seed and bulk idea. So what was that? Well, with very high probability, we first look at a tiny section of A, which remember, this is like the generating set for our random numerical semigroup. So we look at a tiny part of A, and we consider that to be our seed in the whole process, and we call that A naught. And we were able then to see how actually the finite sum generated by A naught, lie in a somewhat dense larger block. And then knowing this, we are able to kind of do this bootstrapping argument, which is like this bulk argument that allow us to then say how basically all that is left is also lying into the finite sum of A. So in particular, how do we do that? We do, yet again, a sort of like splitting argument by first looking at this W's and splitting them among things that are that have small coordinate points and things that are instead of even larger coordinate points. So, and we do this bootstrapping argument for the W1, for the W prime, which, as I said, are the small coordinates point with respect of the finite sum of A naught, to show that they lie in the finite sum of A, and do a similar thing for the higher coordinates point and be able to show that they also lie in the finite sum of A. And then by taking a union bound, this tells us that the region, each of the region UI, and then second union bound, the old region U, which correspond exactly at what's above our hyperboloid, lies in the finite sum of A, which by definition is trivially lying into our semigroup S. And in picture, perhaps to have like a slightly better idea, what I was describing in this last process is exactly this. So we had this tiny like purple box at the very corner left, which is our seed. So we had our A naught box, and we were able to show how the finite sum of A naught, it's somewhat like a bigger box lying around it. And then we do this bootstrapping argument by then looking at points by splitting our high coordinate points W into this purple region that is like made of points that, yes, are away from the coordinate of this log P inverse sort of value, but still not that far away because the coordinate points are less than p minus 2, and then look at what's left. So looking at points whose coordinates are instead bigger than, in this two-dimensional scenario, p minus 2. And we then do this bootstrapping argument on W prime and what's left outside W prime with respect to the finite sum of A naught. Okay, and in this couple of minutes that are left, I would like to just briefly describe some open questions. So I guess the most immediate of them would be about what's going on in between the lower bound and the upper bound scenario. Because as we described in the main theorem, up to this constant factor c, we know exactly what's going on, but we do have this constant factor c appearing. So what is going on in that little tiny region between the bound for the lower bound and curve for the upper bound? So that's the first question that we had. And then the second question that we had is instead considering what is the exact form of the probability at this time we're looking at as a fixed point in our region, and we're asking when do we have that such a point lie in our semigroup S, or correspondingly in the finite sum generated by A, what is the probability for such a point to lie in there? And in particular, we conjecture that this should be, or at least we ask whether this should be of roughly of this form, where the expression in the parentheses is what one should expect, and where with phi of d we mean some sort of quickly decaying function. And I guess that was all I wanted to say for today. So thank you for your attention.
Well, thank you very much. Any questions for our speaker? I actually have a question. So you take your finite set of lattice points, and you look at the semigroup it generates.
Yes.
You could take your set of lattice points, look at the h-fold sum, and then the semigroup is the union of all the h-fold sums. Right? But if you look at the h-fold sum, so if you take your set of lattice points, if you take its convex hull, so you have this lattice polytope, and your set is inside the polytope, and when you take the h-fold sum is sitting in the h times dilation of that polytope. And there has been for a long time a question about how, as you take h bigger and bigger, and you have this expanding polytope and the lattice points inside, how at each stage, at each time h, what is the shape or the configuration of the lattice points inside the polytope?
Oh,
so
I
it
see.
shows up everything within a certain distance to the boundary.
Yeah.
But the boundary behavior is really interesting and somewhat mysterious, I think. And I don't know if anyone has ever looked at that very closely.
Oh, I personally haven't. With Noah, we didn't discuss this case in particular, but it's actually a really interesting question. So I guess it would actually be cool to go back and actually look at this, because I haven't personally have done that, but it sounds really interesting question.
I mean, there's some very old work by a guy in Canada, a Russian guy, Khovansky, from a very long time ago that talks about this, but just a little bit. Anyway.
Okay, I see. Okay. No, that's really interesting. Thank you for pointing that out.
I thank our speaker again. And